Hello and welcome to the session on the mechatronics. I am Professor Khond from Kekewa College of Engineering, Nasik. So today's session is proportional, integral and the derivative, that is PID controllers. Now what is PID controller? Basically in the mechatronics we can have the various types of controllers, that is sensor, controller and actuator. In the controller section there are a number of controller. It may be a microcontroller, it may be a PLC controller, it may be a PID controller, so various types of controller. So and the control systems are there. In the control system there may be a discrete type of control system and the continuous type of control system. So our first point is PID implement continuous type of control, where the output is continuously being monitored, it is measured and then it is feedback and then it is being controlled. So that is what we can say, it is PID implement continuous type of control. Okay, now there may be a number of combinations, so it can be individual type of control, that is P control, I control, PI control, PD control, PID controllers we can implement. Okay, now the third point is, for a system where a precise control or output of the system is to be maintained, a continuous monitoring of such system is essential. Okay, so that is what already we have seen this. So where the precise control or the output is required, in that case we require to have the continuous monitoring. For that PID controllers can be effective. Okay, for example, there is a necessity to continuously monitor and control the fuel tank using the boiler bias power plant. So this type of control can be called as modulating type of control. Okay, so now the next point is, proportional integral derivative controllers are used in most automatic process control applications in industry today to regulate flow, temperature, pressure, level and many other industrial processes. Figure we are seeing a controller, so instead of controller we can represent it as PID controller. Okay, now here it is a PID controller, so it may be it may be a P type, it may be a D type and it may be a I type. So it is P, I and D type of controller. Okay, so closed loop type of controller, we are having a feedback. Okay, now this is what the thing, we can have the characteristics equation where M is the output. Okay, M is the output of the controller. Kp is the proportional gain. Tau d, tau I, these are being called as derivative constant. T, tau I is the integral constant, E being the error. Okay, tau I integral constant, E being the error, then tau d, that is derivative time, then dE by dt, that is rate of error. Okay, so we can have the input as the error and the output as the controller output, that is M. So that is what is the characteristic equation for the series PID configuration. Next one is the parallel PID configuration. In the parallel PID configurations, so the things are in parallel: proportional, integral and a derivative. So wherein we can individual control, we can have the individual control of the controller thing. Okay, we can have the individual control. Okay, next thing, so how it works? So basically the controller action, wherein U is the controller output and E is the error input for the P. So here P, proportional controller output, is proportional to the error. Here integral action, here integral time or integral constant. Okay, so controller output is here in integral representation with respect to the error. In the derivative, so rate of change of error, that is controller output is proportional to the rate of change of error. So that is what the thing. In this case, for the integral action we can also make it in different form, that is rate of change of control output is proportional to error. So if you take an integral, we can have such kind of equation. Okay, now this is what the characteristics of PID controller, wherein the things are in parallel. So parallel type of PID controller, and the basic equation, that is control output, then controller proportional constant, then integral constant, then derivative constant, and the same thing. Okay, so when you, this is in the time domain, this is in the time domain, so dt, that is time domain, so it is being replaced with the s, that is the complex domain. Okay, wherein the so for getting conversion from time domain to the complex domain, we have to apply the Laplace transform. Okay, so there will be three types of things, parameters, or we can three, kp, ki, and kd, three types of parameters. Okay, now for the overview, so p only controller tend to generate offset. So when you use only p type of control, so not combining with any other control, that is I controller, D controller, then so it is sure that we are getting the offset, or there maybe we can say a steady state kind of error. So when you use only I controller, it may be lead to oscillations. You can get the output very fast, but you can have the oscillation. Then the next one is D only controller. So D only controller cannot be used alone, as it cannot give any output for zero or constant error. So we cannot use D only controller alone. Okay. Then P depends upon the present error, that is proportional depends upon the present error. I depends upon the accumulation of past error. So already we have seen that the for the I controller, rate of change of control output proportional to the error. So we are accumulating the past error, and then it will take the action, that is integral time. Okay, then third one is D type of thing, that is the prediction of future error, that is rate of change of error. So control output is proportional rate of change of error. So how the error rate change, on the basis of that the controller will take the action based on the current rate of change. Okay, that is P controller, I controller, and D controller. There. Now this is the most important part, that is transient response in a control system. So whenever it is for the control system, so the characteristics are like this. So we can have the amplitude versus time. Okay, for a system. Okay, for a system working at a particular time, and the system is said to have the amplitude. Okay, let us say we are having the 1 as the fixed time, or we can have the steady state value. So we are supposed to achieve this one. Okay, the system start with the 0. Okay, so it will rise up to this particular point, let us say. Okay, then it will come down, then it will go up, and then after some time it will achieve the steady state. So up from this point to this point, we can call it as transient thing, transient response. After that we can get the steady state response. So in between that we can having the different uh, terms which is related to the time response. So term is, first time is rise time. Okay, rise time, see this one. So how much time we require to achieve this steady state output. Okay, so desired output, this is the desired output. So this particular time being called as rise time. Then we are having the peak time, maximum value, maximum peak can be reached. Okay, so it is peak overshoot, mp is the peak overshoot. Then delay time, means 50% of the time, 50% of the desired output. Okay, then so for the rise time, from 10% to about 100% time, or we can say about 90% time. So that is the rise time. Then settling time, at what time from the beginning it will reach. So that is we can call it as setting time. So different times are there: rise time, peak time, delay time, and the uh, peak overshoot, then settling time, steady state response, and the transient response. So these are what the control action, individual control action. say set point, this is a set point, or we can say it is a desired output. So, wherever if it is no control, then the system will be unstable like this. The system will not be a stable point, so no control. So if you use P action, for the P action, say for 2, so it is for the 2, that is P action. So it is for the P action, we can have the difference. So the difference is nothing but the offset, or we can say it is a steady state error. Then for the I action, so it is for the third. So see, it starts with this blue line, blue dotted line. So number of oscillations being increased if you use only I action. So if you use P plus I, in that case the error will get reduced, the oscillations may be there but the error will get reduced. So P plus I, so oscillations and error being reduced. Okay, so we can comment that if you add P, if you add I with P, then the error get minimized. The oscillations may be there but the error being minimized. Okay. Then P plus D action, for the P plus D action, say 5th and 6th, P, I and D. So again the error being minimized. Okay, the error being minimized. Okay, the oscillations may be there. Okay, like this. Okay, how to adjust the parameters like this. We have to adjust the parameters for getting our purpose solved. So for adjusting the parameter, so there is a distinct procedure being called as tuning of PID controller. Okay, so these are what the desired output, this is our desired output, and that we want our, that is our goal. Okay, so our goal may be obtained by this way, or by this way. Okay, but this is the acceptable stability and medium fastness, that is a good compromise. If you use this kind of, there may be a bad, it may be a poor stability, or a very fast response good but pure stability, that is bad. So if you use this one, very stable good but slow response, so you are achieving the output in last time. So this is a bit compromise. So use of PID and use of parameters. So in controller tuning, so that is called as controller tuning. So we want to achieve this compromise, acceptable stability, minimum fastness. So for the tuning of PID controller, the distinct procedure being called as, that is Nicholas Ziegler method, which is very popular for the tuning of PID controller. So we have to use the MATLAB kind of program, or we can use the MATLAB Simulink, and in the MATLAB Simulink, so there we can adjust the parameters, or there we can adjust the tuning. So there may be auto tuning, there may be a manual tuning. Okay, thank you for this session. Thank you.